Okay, welcome back. Section 2.2, day one. Today we're going to start our polynomial function units. We'll be covering polynomial functions in this section, 2.3, 2.5, and I believe one more after that. So it extends through quite a few sections. It begins on page 123. All right, we're not going to really use transformation so much for these polynomial functions. Okay, so you can ignore that first learning target. Today we're going to focus on these two things right here. I can use the leading coefficient test to determine the end behaviors of graphs of polynomial functions. That's review. You've seen that in Algebra 2. You should pick right up on that once we go through it. You've also found zeros of polynomials before, okay? And use them as sketching aids. And we'll actually just use the graph to check to make sure we're doing this part right. Most of this is going to be by hand, okay? All right, let's get started with those two things, and let's get started with what a polynomial function is. Okay, a polynomial function, what you got to make sure is that the exponents is just a non-negative integer. So positive integer, right? So this can be degree 4, 3, 2, 1, 5, 6, something like that, some type of positive integer. We've been dealing with polynomial functions already this year. Okay, so if I had a Venn diagram of polynomial functions, linear functions. We've dealt with linear functions already this year. That fits the definition of a polynomial function. So do quadratics. So do cubic functions, third degree. Okay, fourth degree, they call that quartic functions. After you get past fourth degree, they don't really have names for them. We just call it a polynomial function. Okay. All right, so here's the graphs of polynomial functions and what they look like. They have no breaks, holes, or gaps. So this has a break in it, or a gap. Okay, also it has a hole as well, so even if I had like a straight line with a hole in it like that, an open circle, that wouldn't work. Okay, and it cannot have these sharp turns. It has to be smooth and rounded. So absolute value function is not a polynomial function. But these are. Okay, it's got to be smooth, rounded turns, and they're also continuous. The domain's all real numbers. Okay. All right, let's go ahead and go on to the next page. All right, now we're going to get into this end behavior of these polynomials and what's called the leading coefficient test. All right, so the end behavior is the behavior of the graph of the function as x approaches large values, right? Positive infinity or negative infinity. The graph will eventually rise or fall without bound. Okay, now you kind of want to start in the middle. That's something you may even want to put in your notes, that you describe from the middle. So what I mean by that, if we look at this first graph, we've been taught in previous sections that we call this function to be decreasing from left to right. And now it transitions to increasing, to decreasing, to increasing. So I don't want to do this from left to right and say that that's falling. Okay, we kind of describe the rise or fall from the middle of the graph going out. All right, so from the middle going out, what is this doing? Okay, well, going to the right, this rises. So we'd say this rises right. And then going to the left, the graph is rising again. So this rises left as well. Okay. Pause for a moment, see if you can think about the next one. Moving out from the middle, what is the end behavior of the graph? Okay. Okay, so remember, you focus on this part. What is the end behavior? What's this part of the graph doing from the middle? So it's falling. Okay, so we say it falls left, and then as we trace this graph going off to the right, focus on that part of the graph. What is it doing? It is rising when it's going to the right. Okay. All right, now we can make this determination without even seeing the graph. We can actually just look at the equation and figure this out. And this is where the leading coefficient test comes into play. I really feel like they misnamed this. I feel like they should call this the leading term test because we're going to use two things in the first term, not just the coefficient. The coefficient is the number out front, but we also need to analyze the degree. Okay, so we want to look at the degree and we look at the coefficient when making these determinations. Okay, so let's start off here when the exponent is odd. Let's actually do a little parallel with y equals x cubed. That's a function that we're familiar with. We had to do transformations with that before. Y equals x cubed looks like this, the parent function, right? Okay, so the exponent 3 is odd, and a is referring to the coefficient. Right now, the parent function, the coefficient is positive 1. So it fits this rule. Okay, going to the right, it's going to rise, and going to the left, it's going to fall. Every time. Okay, it could look like this. Y equals x cubed plus 2x squared plus 5, or 5, okay? I can ignore all this. All you got to do is focus on the leading term. Okay, so since this is positive, and that's 3, this graph will look the same as this one for the end behavior. Okay, it might do different things in between, all right, but the end behavior is consistent. And that's why these graphs have these dotted lines, right? Y equals x cubed and x squared plus 2x plus 5 will look different here, okay? But predictable for large values of x. Hopefully that makes sense. Can't explain it any differently. Okay, and then just the opposite. If I were to talk about this parent function and say, all right, now it's going to be y equals negative x cubed, what would we notice about that parent function? It's just going to be turned around this way. Okay, so now it rises going to the left, it falls going to the right. So here's your rules. Rises left, falls right. So you can look at the word rules or look at the picture rules if you want. Okay. All right, so quickly get through these evens now. I'm pretty slow on the odds. Evens, okay, basically if it's an even exponent like y equals x squared or x to the fourth, and the coefficient is positive, okay, it's going to end like this. It's going to rise in both directions. Different things in between, but this will be predictable. And then if you make the coefficient negative, it just flips upside down, okay? Falls in both directions. All right, easy enough. Number 3 and 4, I'll walk you through and then have you try the next few, okay? All right, so I can ignore this part. I just want to analyze negative 2x squared to describe the end behavior. Okay, it says left hand, right hand. They just mean if you're going to use your left finger and your right finger. All right, so going to the left, going to the right from the middle. Okay, so since that has an even exponent, right away I'm down to one of these two. Okay, and since it's a positive, I'm sorry, it's not positive. Since it's a negative coefficient, it goes to this rule. Okay, so it's going to fall in both directions. So this falls left, falls right. Now, if you want to say falls left and right, fine. Okay, but for whatever reason, they kind of usually make two statements in the book. Okay. All right, moving on to the next one. All right, maybe I should be more specific about this too. Right now, we have n equals 3, so it's odd. And a is negative, right? A equals negative 1, so a is less than 0. Okay, back here, we had n equals 2, even exponent, and the a value was negative 2, which is negative, so a was less than 0. So those are the rules we're following, even and this. This one is odd and this. Okay, so this going to the left from the middle, it's going to rise left, and it falls right. Okay, your turn to stay engaged and participate. Pause the video and try the next, how many? 5, 6, and 7, I think. Go ahead. Okay, here's your feedback on this. Falls left, rises right. If you didn't get that, recheck your rules. Positive, and it's odd, right? This one is an even exponent, and it's positive again. So this is going to kind of do the horseshoe thing. All right. rises in both directions. Now this one, when it's in factored form, what you need to do is, maybe you can do some of this in your head too, but if you need to multiply some of this out by hand, the shortcut to figure out the degree is take this second degree and add the 1 degree here, so it's third degree, but do we know the coefficient by doing that? Maybe not. So here, let me show you how we could start multiplying this out. X plus 4 squared is equal to this. And then I got to multiply by x minus 3. So I just take this x minus 3 and distribute that. Take the x, multiply it through, and then take negative 3 and multiply that through. So x times x squared gives me an x cubed. Okay, that's going to be the largest term. I can keep going if you want me to, right? Plus 8x squared plus, all right, I have more terms. Okay, but, sorry, I was interrupted there. All right, so we have the leading term. Like I said, we don't have to finish multiplying this out. X cubed is enough to make the determination that it's going to fall left and rise to the right, okay? All right, so that is the leading coefficient test. Let's move on to the next learning target of finding zeros of these polynomials. Now, there's a lot here. There's a lot of characteristics of these zeros of polynomials. So let's go over it right now. Okay, the maximum number of zeros of a polynomial is the degree of the polynomial. So for example, this was a third degree function. It can't have any more than 3 zeros. This was a fifth degree function. It can't have any more than 5 zeros. Okay, and so on. It just so happens that the location of the zeros, sometimes called roots, are always at the x-intercepts of the graph. So you can use that to your advantage. Okay, 0 also has multiplicity. Let me just go back to a real basic function we've been dealing with to talk about multiplicity. If we had this quadratic and we were asked to find the solutions, or we're going to call those zeros now, we replace y with 0, and that's why they call it zeros. It's any number that when plugged in gives me 0. Okay. All right, so this one is factorable. So I could factor it to x plus 5 and x plus 1. And then I'd say my solutions are, or zeros are, we could say negative 5, because we should be, using the zero product law, right? I guess I'm skipping that step. Set that one equal to 0 and set this one equal to 0 and solve them. Subtract 5, subtract 1. So we'd say negative 5 and negative 1. Now these have multiplicity of 1 because they only happen once. Now we weren't stating multiplicity in our quadratic unit because it was kind of obvious. We knew they both had multiplicity of 1. All right, but it always kind of just tracks back to the exponent of where that 0 came from. They were both an exponent of 1, so they have a multiplicity of 1, okay? All right, so for this particular problem, okay, it happens 4 times. This one's already factored 4. Sometimes they won't be, sometimes they will be. And if they're already factored, it's pretty easy to find the zeros because we're supposed to set both of these equal to 0 separately. So I've got x minus 2 equals 0, and I've got x plus 3 equals 0. I don't have to write it 3 times. I don't have to write that 4 times. That's the idea of multiplicity. So I add 2, and I get this 0, right? X equals 2 is a 0. What's the multiplicity of it? 4. Okay, so we just need to write that in there. It has a multiplicity of 4. Okay, this one we get a 0 of negative 3. What's the multiplicity? It's 3. Okay. All right, and we know this is a 7th degree function because we can add those exponents. We don't have to multiply it all the way out. 4 plus 3 will give us that. Will give us the fact that it's a 7th degree polynomial. Okay. One other thing I skipped here. At most, it can have n minus 1 turning points. Okay, so that's why it says it can have at most 6 turning points. You simply take the degree of the function and you do the 7 minus 1, right? 6 turning points it could have. It doesn't have to have that many. It's the most it could have. Okay, one other thing I want you to add, I want you to write it right here about multiplicity. I'm going to pause the video and start the second one right now.